So SPC6 is on something fantastic known as the photoelectric effect. This is actually what won Einstein his Nobel Prize. None of that E equals mc squared stuff. It was this photoelectric effect that actually won him that prize. And it builds a lot on some of the stuff we touched on at the end of the MUS module. You'll recognise the Planck equation here, which we'll be revisiting and using it in a couple of new ways to explain this photoelectric effect, which is unfortunately we can't demo it in this video, but it'll be demoed for you in class. But hopefully we can at least discuss a theory here and give you an idea of what's going on. So as you'll see in the class demonstration, the photoelectric effect is essentially where we have some metal plate, some photons are instant upon this plate, and that releases some electrons off of it. So photons instant on plate, plate emits electrons, nice and simple. This links nicely in with photovoltaic cells or solar cells. So within a metal we already have lots of free electrons, and so when the photons are instant upon the electrons, they're emitted. But within solar cells we have semiconductors instead. Within the semiconductors, rather than having the photons emitted, having the electrons emitted, what we have is the electrons become freed from their host atom, and they're now able to move freely within this material, and that's part of the process that turns this light energy into electricity. So let's have a slightly closer look at what goes on. So as we said, photons are instant, electrons are given out or might be given out. So photons in, electrons out, and we'll see that there's some threshold frequency. So it's not any light instant upon this metal releases an electron. The light instant has to be a certain frequency, at or above a certain frequency, in order for the electrons to be given out. So let's have a look at the two different interpretations. So we've got a classical and a quantum interpretation of light. That's the wave model is the classical interpretation, and the photon model is the quantum interpretation. So let's see what sort of predictions these two models would make, and hopefully we'll see some interesting results when we do so. So starting with the classical, we've got the waves, they're instant on the metal, and we've got these continuous waves pounding into the metal, and gradually the energy is going to build up into the electrons. So what we'd predict is that no matter what the wave is, no matter the frequency, is going to be instant upon this these electrons. The electrons will gradually gather the energy from the waves until they've got enough energy to escape from this metal, from the metal surface, and go flying off. So we predict there'd be a delay between the instants of the light. So because we've got to wait for the energy to build up, certainly if we had a lower frequency with less energy associated with the wave, we'd have to potentially wait quite a while for enough energy to build up for the electron to escape. And it also predicts that any frequency will be able to release the electrons. So anything from gamma rays all the way through to radio waves at the low end of the spectrum would be able to cause these electrons to release, would be able to cause this photoelectric effect. And as we increase the frequency, we're going to increase the rate of the energy being instant. And so if we've got higher frequencies, the electron is going to be released more frequently. The quantum interpretation has something quite different. So now we're modeling light as the photons, as single photons rather than these waves. And so rather than the wave gradually building up into the electron until it's got enough energy to escape, an electron absorbs a single photon, and then the energy of that single photon, given by the Planck equation, which we're so familiar with, so that was the E equals hf. So there's the energy of the photon and the frequency of its wave equivalent. So we've got single photons instant, and that means that The electrons only get released if this single photon has got enough energy to let it escape. So that means that there's going to be a threshold frequency, that we require a minimum frequency so that this single photon has got enough energy for the to pass on to the electron for it to escape. And we'd also predict that if we increase the frequency, well, we still only got one photon interacting with one electron. We can't have one photon suddenly interacting with multiple electrons, so we're still going to have the same rate of electron release. But what's going to happen is there's going to be more energy left over. We'll have a look at an energy equation in a minute. There's going to be more energy left over, and so these electrons, rather than coming off more frequently, they're going to come off with more energy, so they'll come whizzing off when we increase the frequency instead of there being lots of them. In order for us to increase the rate of electron emission, what we'd have to do is increase the intensity of the light. So we could keep the frequency the same, but simply brighten the lamp that's illuminating it, and that would increase the number of photons, and therefore increase the number of electrons that we could have coming off. So Einstein, he didn't just look at this and write a few interpretations. He of course came up with a lovely equation, and the equation boils down essentially to an conservation of energy issue. So if we come back to here, we can have a little think about it. So let's clear this off for a moment. So the conservation of energy means that the energy can't go anywhere. So we've got some energy in, which is going to be from the photon, and that must equal whatever energy comes out. So the energy will come in the form of the photon and go out in the form of something else. So the energy in is just going to be the energy from the photon that we had from the Planck equation. And that energy is going to go into where? Well, it's going to go in two places. One is the electron's going to come flying off. So the electron has some kinetic energy. So that's going to be half mv squared. But then the electron also uses up some energy in escaping from the metal surface itself. So if we imagine our metal surface, if we if it was previously neutrally charged, if we now take an electron and pull it out, that's going to leave a host atom with a positive charge left there. And so there's an attraction between these two. For the electron to come off, we've got to overpower this attraction. We've got to put some energy into the system. And we call that the work function, which unfortunately requires yet another Greek letter, the phi. And so we say that the energy in from the photon goes into the kinetic energy of the electron plus the work function, so the energy involved in escaping in the first place. So we can see that this work function is going to be constant. It's going to be the same for a given metal. So the energy required to take an electron out isn't going to change. It will have different values between different metals, but within one metal it's going to be the same. Nothing's going to affect it. So if we increase the frequency, the only thing that can increase on this side is the kinetic energy. So if we go for a higher frequency, then our electrons are going to come whizzing off faster, because of course we can't change their mass, at least not as far as you're concerned, until you get onto relativity. But anyway, right, what have I been writing here? So here we go. We said there's a threshold frequency, so the single photon has to carry enough energy. So if we have another look at this equation, this is the energy of the photon, and if the photon doesn't carry at least enough energy to overcome the work function, to overcome the energy to escape, then the electron's not going to escape. It's only the bits left over that go into the cave. So at a minimum, we have to have the energy of the photon equal to the work function. And so we can use this to work out the threshold frequency. The frequency must be at least this high in order to escape from the metal. Anything less and we don't have enough to escape. Maybe we'll just warm up the metal a bit, but we won't have any electron emission. So that's what our work function is. It's what we need to get out. And it's only the leftover then that again goes into the kinetic energy. So here we have it in word form and the other way around. So there's the photon energy, and so we have the energy of the work function plus the Ke has come from this photon energy. And here we have the equation written down in a slightly alternative form. This max bit is a bit interesting, because on the way out, electrons are going to lose a bit of energy. So here in our diagram, we've taken an electron from the surface, but if an electron has been emitted from a bit deeper down, say around here, then on its way to the surface, not only has it got to come overpower this attraction to its host atom with the positive charge, it's also got to find its way out through all the other atoms in a similar manner to the source of electrical resistance. So the electrons kind of squeeze through a wire, experience some resistance. And so the ones at the surface are going to have the maximum amount of energy. The ones below, the work function is still the same, but it's going to have a larger effective value because we've got the work function plus a bit of energy to escape the metal, and then what's left over goes into the kinetic energy. And so what's in the kinetic energy is going to be a bit lower. So this equation balances when we look at the maximum kinetic energy of electrons coming up. So if we were to illustrate that, if we had some electrons and their kinetic energy, so this would be the number of electrons with some amount of kinetic energy, there's going to be a maximum amount of kinetic energy which they have, and there'll be some electrons with that much, and then the rest will have some lesser values. So these are the ones which are right at the surface and haven't had to fight against anything but the work function. These ones have had to fight against the work function and make their way out through the metal. So they've lost a bit more energy and have got less kinetic energy left over. So that's why we use the Ke max in that equation. So this is the photoelectric effect. This is a really fundamental discovery in physics, because it can only be described when we model light in the photon model. If we try and make predictions using the wave model, we saw that comes up with inaccurate predictions. We predicted we could put in any frequency and electrons would come off, but that's not true. We need this threshold frequency that is quantified in this equation. And so this is the quantum nature of light, the particle nature of light, that light has to be made up out of photons, not waves as we previously thought. And that's a really fundamental thing, and it led on to a whole world of other issues that arose from that, of quantum physics and quantum mechanics. Maybe not completely stem from this, but certainly very closely linked to this. It's a really fundamental, one of the early parts in quantum mechanics. So very important and quite a profound discovery, certainly worthy of his Nobel Prize. That's not to say all the Z equals MC squared stuff wasn't any good. Anyway, that'll do for today.